We quite often come across derivative operators in quantum mechanics. For example, our simple Hamiltonian in Schrödinger's equation has the second spatial derivative, and the momentum operator has a first spatial derivative. Now, if these are operators, then we should be able to write them as matrices. On the face of it, this may seem a strange thing to do. First of all, though, from a fundamental point of view, we should do this for conceptual completeness. Secondly, in fact, in numerical calculations with derivatives, we actually do this all the time, even if we don't explicitly point that out. A third reason for looking at this matrix form of derivative operators is that it enables us to draw some conclusions about the mathematical nature of derivative operators, some of which are quite surprising and important in quantum mechanics.
So let's look then at the matrix form of derivative operators. We return to our original discussion of functions as vectors. We can postulate a form for the differential operator. So this is our postulated form of a matrix to try to represent a derivative here, d by dx. Why have we chosen that? Well, we presume we can do this. We're going to take the limit as delta x goes to 0 here, and this will match up with our idea of a function as being determined by a set of values at a set of closely spaced points spaced by delta x. So if we multiply a column vector whose elements are the values of the function at all of these closely spaced points separated by delta x, if we look at what happens when we multiply this in here, then what we'll find is the resulting vector has got elements like this in it. But this element here is just the derivative df by dx near xi, and this one is just the derivative df by dx near xi plus delta x, and so on. So indeed, this is a good representation of a derivative operator represented as a matrix. And again, we're taking the limit as delta x goes to 0, as we need to do in order to take derivatives. Hence, we do have a way of representing a derivative as a matrix. And this is something that we end up doing all the time when we work with the computer. Now note something about this matrix. This matrix is antisymmetric in reflection about the diagonal. So we've got 1 over 2 delta x here, but we've got minus 1 over 2 delta x here. We could call that an antisymmetric reflection. And it's not Hermitian. This element here is not the complex conjugate of that one. This is minus that one, not the complex conjugate of it. In this case, since this is real, the complex conjugate of this would just be the same thing, but we've got a minus sign here. Indeed, somewhat surprisingly, this operator, d by dx, is not Hermitian. And if you just look at that, that might take you by surprise, because Hermiticity's got something to do with complex conjugates. This looks a perfectly real kind of operation, and hence we might not expect to run into trouble with complex conjugation. But in fact, d by dx is not a Hermitian operator. We can run through similar arguments for the second derivative operator, and if we do that and we construct a corresponding matrix, we would actually find that the second derivative operator gives us a symmetric matrix with real elements, and hence it is Hermitian. So if we didn't put together this matrix form, we might have missed this point. d by dx is not a Hermitian operator, but d2 by dx squared is a Hermitian operator. Finally, let's point out one formal point. If we are operating on a function by just multiplying it by another function, such as a potential, for example, to generate a new function, g of x, then this v of x is performing a role like an operator because it's taking one function and turning it into another one. It's a particularly simple version of an operator, but we could view it as an operator if we want to, and we could represent it as a diagonal matrix whose diagonal elements are simply the values of this function v of x at each of the different points. So it could be a diagonal matrix with v of x1, v of x2, and so on all the way down the diagonal. If v of x is real, then this matrix is Hermitian, as required for it to be part of a Hamiltonian. So when we write out a Hamiltonian with, for example, our kinetic energy term minus h bar squared over 2m times del squared plus our potential energy term v of x or r, whatever, we can think of that v as being an operator also if we think of writing it in this diagonal form. So that whole entity becomes our Hamiltonian, and it is indeed the sum of two operators. This is only a formal point here. It doesn't make any difference to any calculation, but it helps straighten out a minor issue with the operator form here of the Hamiltonian.